Okay, can everyone hear me out there? So what we're going to do today is really just get into the nuts and bolts of nomenclature. So I have a whole slide deck presentation that I give if we were face-to-face, so I thought I would just do that. And so essentially, we're going to look at pretty much get through the nomenclature for all the functional groups. And so I'll give you the actual IUPAC rules for nomenclature, and then we'll go into some basic stuff in terms of me lecturing on nomenclature, but the majority of the chat session will be spent by you guys looking at structures and naming them. The best way to figure out how to do these problems is just doing them. So looking at the actual rules, in my mind, it's you need to know them, but like memorizing them or committing them to memory is not the best use of time. So let's go ahead and we'll get right into it. So these are the basic nomenclature rules, and as you can see, they're pretty long and wordy. So I think the best way to learn this is just by doing problems, and I'll explain these things. But the main thing is you have to know basically the first 10 hydrocarbons. So from C1, which is methane, all up to C10, which is decane. So you have to know those and then know derivatives of those. So basically, when you're given a compound, you identify the longest chain, then you associate that chain number with a parent alkane. And so then once you find the longest chain, we're going to number it in such a way that everything on the chain has the lowest number. And things hanging off that chain are called substituents. So basically, you're going to name the substituents in alphabetical order with the number associated with which carbon chain. And so that's sort of up to 1 through 3. When we get to 4, that's when there's more than one of the same type of substituent present. And you have to use things like di to indicate 2, tri to indicate 3, etc. So basically, we're going to go through pretty much all the functional groups you've learned so far, the hydrocarbons, then we'll get into alcohols, amines, then the oxidation state 3 functional groups. So let's just go ahead and get into it. So I'll refer back to this slide as we go along, because it's important to know that specifically what substituents are. So substituents that are hanging off the main chain can be named as these things here. These are common names. More specifically, you'll want to know things like an OH group is called hydroxy, OCH3 is methoxy, and so on. So if you see this sort of Lewis thing, this is the associated word for the substituent. Another important thing is the functional group priority. So if you have a compound with more than one main functional group, how do you know how to name the sort of parent of the functional group? They follow this order here, and I'm going to switch over to the document camera, and this is in your workbook, the first semester topics. The functional group, they basically follow this priority. So what that means, if you have say two of these things in the same molecule, which one gets the parent name? So we're going to start with alkanes, and so I don't think it should be a big surprise to you. This sort of box here, where you have your carbon count from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alkane ends in ane, and so these things are named. So 1 carbon is methane, 2 is ethane, and then this is sort of the condensed formula. 3 propane. So what we're doing, these are called homologs, and what happens in each subsequent one, the number of CH2 groups increases, and remember we called those methylene groups. So you pretty much have to know these. So if you're given octane, you know that that's 8 carbons. So alkenes, we have now a degree of unsaturation. So you can't have a 1 carbon alkene, you have to have 2 minimum. So now you have this CH2, CH2, and the double bond, so that's ethene. Notice ane for alkane. Alkene, now that A changes to E, so you have ethene. So it's basically the name sort of stays the same, but you change the vowel here. And so that's what I mean by sort of the suffix of the name. So this ene tells you that there's an alkene in the molecule. So basically you go down through your 10 hydrocarbons. Alkyne now has a triple bond. So ethene, we remove 2 hydrogens, that becomes ethyne. So YNE, YNE. So the first part of the name is telling you how many carbons there are. So 2 carbons. The suffix is telling you what the main functional group is. So this is an alkyne. This box here is telling you what those specific carbon counts are when they're substituents. So if you have a 1 carbon methyl, so the ane now becomes YL, so methyl. This you've seen before. So a primary carbon, it's bonded to 1 carbon, so that's sort of like a methyl, right? Secondary, bonded to 2 carbons, so that's methylene. So this stands for carbon and hydrogen. So methine, tertiary, we see that here, and then quaternary has 4 carbon atoms. So I have a couple more slides with different functional groups, but let's sort of get into the problems. So here's a typical question for organic chemistry. You're given a structure. What is the name of that structure? So that's what we mean by nomenclature. It's ways of communicating in the language. The screen is glitched. So what? Let me try this. Did that help at all? Still glitchy? It did not help. So we got a couple people saying it looks fine. Works now. Okay, so maybe it's just a temporary internet thing. So maybe Ian, try logging off and logging back in. So we have this structure here, and we want to figure out the name. So the first thing that we want to do is count the longest carbon chain. So I'm going to switch over to the document camera. So the first question I want to ask you when you look at that structure and you count the longest carbon chain, how many carbons are in that chain? So we'll wait till a couple more people respond. So yeah, it should be 8. And so what is the burden on you as the student when you're doing this type of problem? You have to count the different sort of routes of that chain. So what do I mean by routes? Say I start at this carbon. I start counting 1, 2, 3, 4, 5, 6, 7, 8. So just because I did something once doesn't mean I'm done. You have to do it a couple different ways. So what if I start here? 1, 2, 3, 4, 5, 6, 7, 8. So that's also 8. What if I don't really know what's going on and I start here, I go 1, 2, 3. So that's obviously not the longest chain, right? I mean, you can just tell just by visualizing that. What if I start, say here, 1, 2, 3, 4, 5, 6, and I stop there because this sort of looks branched? Well, that's not the longest chain either. So when you're doing these, you have to consider a lot of possibilities. So we say 8. So remember what the alkane name for an 8 carbon chain is. Type that in the chat box. You have 8 carbons. What's the alkane name? So it's octane. So octane is your parent. And so if you're given this, just these words, octane, you can read the suffix of the name, ANE, and it's telling you that it's an alkane. So if you further think about that, it's C plus H, and it's fully saturated. So don't forget all that stuff when you're just thinking about these sort of fairly simple looking things. So we found the longest chain. So in the salmon fuchsia colored marker here, whatever, I'm going to circle that chain. So I circled that, right? So with the purple marker, everything outside of that chain is called a substituent. So maybe what I'll do is I'll put like a star, an asterisk by the substituents. So if you look, how many carbons are on those substituents? So there's 3 of them. Yes, that's correct. But just consider the one substituent itself. I mean, they're all the same, right? how many carbons are there, right to where the marker's pointing? So I'm back on the screen here, and I say it's a 1 carbon substituent. So see where my mouse is pointing, there's 1 carbon, right? So that substituent is called a methyl group. So that's where that comes from. So a methyl substituent is this, CH3. So you have CH3, CH3, CH3. So there's 3 of them. So sort of if we're going by this this rules here, we're on step 3 where it says indicate the substituent location by its numbered location on the longest chain. So this is where we circled the longest chain, right? But now we have 2 ways of numbering that chain. So in the green marker, I'm going to show you the correct way of numbering the chain. Then we're going to go back and number it the other way, which is incorrect, so you can see why it's incorrect. So I'm going to start the numbering here. So 1, 2, 3, 4, 5, 6, 7, 8. So every carbon in that circle got a number. And the reason we do that is to identify where these substituents are. So in the chat box, why don't you type a series of numbers separated by comma that tell you where those 3 methyl groups are. So you should write 3 numbers in the chat. So we have 2, 2, 7. So we have 2 methyl groups on carbon 2, and then 1 methyl group on carbon 7. So if you look down to rule 5 here, when 2 or more substituents are identical, indicate using a numerical prefix. So we have 3 of them, right? So we're going to use try. See how we have 1, 2, 3. These numbers indicate the total number. So we say try methyl. 2, 2, 7, trimethyl. So those are all the substituents on that chain. So what we then do is put those substituents with the parent name. 2,2,7 trimethyl octane. So one of the skills that you'll need to build throughout, this module in Organic 1 and 2 is not only figuring out the name when you're given a structure, but if you're given the name, what is the corresponding structure? So when you read this 2,2,7 trimethyl octane, you can see these there's sort of a natural break here. Those are substituents. And this is the parent. These numbers, 227, are called locants. So what it's telling you is the location on the longest carbon chain where these three methyl groups occur. So as I said, it's really best to do as many of these as you can. So any questions on this before we consider another one? So we're back on the screen now. If you look, you have this structure which has a ring. So my first question to you is, how many carbons are in the ring? So there's 6 carbons. So a 6 carbon unit is normally hexane, right? But since we're in a ring, the parent is going to be cyclohexane. So with the pink, I'm going to circle the longest carbon chain, which is a ring. So we got 6. That's how we get cyclohexane. Now let's identify the substituents. So let me click back over to the substituent slide. So I'm in this sort of second box here. So this group here as a substituent, what is that called? So it's a bromine atom, but as a substituent, it's called bromo. As we saw in the prior slide, we have a 1 carbon unit that's called methyl. So the difference between the prior problem and this one is you now have 2 different substituents. So what order do they go in? So you look at the first letter of each. This is a B, this is an M. So alphabetical B occurs before M. So we're going to list them in terms of the bromo being first, then the methyl. However, we're still not done yet. We have to identify where each of those occurs on the ring. And so in this scenario, what we're going to do in terms of starting the numbering, because the B occurs before M, we're going to call this position 1. Because we have to assign all the carbons a number, in this case, we're going to go 2, 3, 4, 5, 6. So based on that information, what should the name of this compound be? So look at the screen, type in a letter into the chat box about what you think the name of the compound should be. So it is 1 bromo, 3 methyl cyclohexane. So let me point out a couple more subtleties about this process. So we said the number is the locant. The one carbon has the bromo substituent. The number and the substituent are separated by a hyphen. So these two go together. They are then separated by another hyphen. The 3 is associated with the methyl. There's no space between the substituents in the parent. So the correct answer is 1-bromo, 3-methyl cyclohexane. So Hannah asks about, could you go around the other way with the numbering? Which reminds me, I forgot to do that on the other slide, so I'll go back to that one and do it as well. So let me redraw it, and we'll go the other way. So there's the compound again. I circled the cyclohexane. Now in the red marker, I'm still going to start the bromine at position 1, but instead of going counterclockwise, I'm going to go clockwise. 2, 3, 4, 5, 6. The bromo and the methyl, in terms of the names, don't change. What will change is the following. 1-bromo. Now it will be 5-methyl cyclohexane. Now the reason this is not the correct name is the following. If you take these two numbers here, 1 and 3, 1 plus 3 is equal to 4. Now if you take these two numbers here, 1 plus 5 is equal to 6. 6 is greater than 4. So the reason that this is not the correct name is because you've given the locant numbers a higher number. And as part of our rules, so it's sort of like rule 7 here. When you number these chains, you want to give the substituents the lowest possible numbers so that their sum is the lowest number possible. Any questions on this before we move back to the first alkane, and I can show you why numbering the chain the other way is incorrect in that example? So I did this correct in green to begin with. I put the numbering 1 here. Let me redraw that compound. And so what if you were to number the chain the other way? So we started down here, 1, 2, 3, 4, 5, 6, 7, 8. Now what if we started up here, 1, 2, 3, 4, 5, 6, 7, 8. Given this information, how would you then name this? So maybe in the chat, using this numbering scheme, name that. Then sum up the locant numbers for that versus this. So you can see why this numbering scheme is incorrect. So using this numbering scheme, name the compound. Then sum up the locant numbers and see what you get. So yeah, here you get 2,7,7 trimethyl octane. So when you sum that, you have 7 plus 7, 14. That gets you 16. 16 is greater than 11, so this is the correct response. The other thing I want to point out from this problem here, so the numbers, see these consecutive numbers, 2, 2, 7, the numbers are separated by a comma. When you get to the terminal number, that's where the hyphen occurs. 2, 2, 7 hyphen substituent parent. Any questions on that one? So let's look at the screen now. We see another difunctional compound. So the hyphen occurs at the hyphen occurs after a locant number, before the substituent. So let's apply the same rules. So given this compound, what's the longest carbon chain? How many carbons are in the longest chain? So if we count 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. It's 7 no matter which way you count it. A 7 carbon chain is what name? So going back to we see that 7 carbons is heptane. So when we circle that, we can see that within that 7 carbon chain, there's a pi bond, right? So this name has to then be modified. So this was we're getting the sort of the base number. 7 is heptane. We see the presence of the pi bond. So now we know we're dealing with an alkene. So the ANE becomes ENE, heptene. So the ENE tells you there's a pi bond. But now what's the issue is where does that pi bond start? So knowing sort of the things we just went over, we have to put a number, then a hyphen in front of this to communicate where the start of the pi bond is. So what do you think that number should be that indicates the start of the pi bond? So a couple of responses say 3. So 3 heptene. The 3 tells you the start of the pi bond. So 1, 2, 3, 4, 5, 6, 7. Again, the 7 tells you it's a C7 chain. Heptane, we see there's a pi bond, so it's a heptene. The 3 is telling you it starts at position 3. 3 heptene. So now the substituents we've seen before. This is a methyl. This is a bromo. We have B and M. So we have, in terms of alphabetical order, B is greater than M. So we have 3 bromo, 2 methyl, 3 heptene. So that all becomes one long word. Three bromo, 2 methyl, 3 heptene. There's one more piece of information. If you look at the screen now at the potential answers, you see at the front of those potential answers, you see the words cis and trans. And really what that indicates to you is in the alkene pi bond between 3 and 4. What I'm going to do now, what I haven't shown, I'm going to show this hydrogen. The words cis and trans relate to the relationship of the substituents on the pi bond. So we said that 3 and 4, those are the sp2 hybridized carbons of the pi bond. Now what we're going to do, and maybe I'll just redraw this so it's a bit clearer. Because all of the substituents directly bonded to those carbons are different. See, you have 3 carbons here, you have a bromine, you have a hydrogen, then you have 3 carbons. They're all different. So now what we have to do for each one, so for this one, you have bromine directly bonded to it, and then you have carbon directly bonded to it. We're going to assign a priority. The priority is based on atomic number. So let me open the periodic table real quick. So you can see carbon has an atomic number of 6. Bromine has an atomic number of 35. And so what we're doing here is we're saying the group that gets the highest priority is the highest atomic number. So 35 is greater than 6. So we're going to call this priority 1, and that's priority 2. So when I'm just going to put a 1 here and a 2 there. So now if we do the same thing for the other carbon, we have C and H, hydrogen's atomic number 1. Carbon is 6. 6 is greater than 1. So this gets the top priority. Hydrogen gets the second priority. And now what we're looking at is the location of the two number one priority groups. See how they're on the same side of the alkene? They're both on the same face. The word that we use in organic chemistry for same is cis. You'll also see in your book a one letter sort of way of denoting that called Z. Cis or Z means that those highest priority are the same face of the alkene. So the correct answer for this one is C. Cis 3-bromo 2-methyl 3-heptene. Any questions on this? What I've drawn below here is this same compound, but now I've reversed these priority groups. The one is still there. Now the one is on the opposite. See how the one groups are now on the opposite faces of that alkene? So we would name this compound as trans 3-bromo 2-methyl 3-heptene. So the difference between them is this cis and trans. Another thing you'll see in your textbook is E for trans. So notice that the entire name is the same except what is in front here. And that is important for denoting the relationship of those high priority groups. Because they both have 3-bromo 2-methyl 3-heptene, right? So this cis or trans is telling you the relationship of those groups about the double bond. And recall the reason that's important is because there is restricted rotation. About a double bond, meaning this structure and this structure do not interconvert. They are different structures, and so we have to name them differently. Questions before we move on to another functional group? So for this one, look at the structure and consider all the rules we've just went over and see what you think is the proper name. So in the chat box, type A, B, C, or D about what you think the best name for that compound is. What are some other? We got some debate against D as in dog and B as in boy. One of those has an issue, and maybe we can explain why one of those is not preferred. So the correct answer is D as in dog. And so I think the choice between B and D illustrates an important point to bring up or discuss why B is not correct. So the choice is the correct answer is 5-methyl-2-heptanol. So we number 1, 2, 3, 4, 5, 6, 7. So 7, that's where we get the heptane. The major functional group is an alcohol. That's at the 2 position, 2. Then the alcohol is OL. So we can see on this slide that has alcohols, ether, amines, and alkyl halides. We started with heptane. We see that the major functional group is now an alcohol, OH. So now we have heptane, the E becomes OL. The OL tells you it's a hydroxy group. The 2 position tells you the location of that alcohol. And then everything else is a substituent. So the 5 position has a 1 carbon unit, that's methyl. So that's how we get the 5-methyl heptanol. So again, in the breakdown of these things, you're getting this from the longest carbon count. And then sort of the suffix is going to change based on the priority group that is present. So in this one, the OH is the priority group. So we know OH as hydroxyl. When it becomes the parent, it's an alcohol, and that's where we get the OL. Any questions on the alcohol? Again, the reason why B is not correct is because it's assuming that you're starting the numbering here. 1, 2, 3, 4, 5, 6. But that's not the longest chain. Again, the rule number 1 is finding the longest chain. So look at the compound that's shown now. So first things first, what is the longest chain? So it's 7, so it's heptane. But now you have things other than carbon substituents. And so how do you figure out what this should be modified to? And so I'm going to click back up to this slide here. See where it says functional group priorities? And what you can, the way these things are prioritized, the way that I like to teach it and think about it is according to the oxidation state. And what do I mean by that? So other than the carbon-carbon, carbon-hydrogen bonds, what functional groups are present in this molecule? So in the chat, I'm looking for 2 main functional groups present in this molecule. So aldehyde and haloalkane. We're using the terminology on the slide. So yes, as a student, you can memorize this list. But what's another way to make sense of this list? If you have something that has multiple substituents, how do you know what the parent is going to be? So see this carbon right here? This carbon bearing the heteroatom of the aldehyde, if you count the number of bonds to that heteroatom, you have 1, 2, correct? I'm just counting 1 bond, 2 bonds. Now look at the carbon here bearing the chlorine. That's just 1 bond, right? So to understand this functional group priority list, you're really looking at the oxidation state. So functional groups 1 through 5 here, those are all oxidation state 3. Aldehyde ketone are oxidation state 2. So we just saw that. All we're doing is counting. Alcohol, amine, those are oxidation state 1. This is oxidation state 1 here, but notice it has a much lower priority. So that sort of throws a wrench in the works. And then from here, alkene, alkyne, alkane. So really, you're looking for the presence of heteroatoms. Those typically dominate in terms of transforming this into. So if the aldehyde has the priority in terms of the name, 2 is greater than 1, it says the suffix of the parent should now change to al. So what should we change heptane to? So we're going to drop the E. So we're dropping the E in heptane and we're adding al, so heptanal. The thing about an aldehyde, the aldehyde always has to be at position 1 in the longest carbon chain. This has to be position 1. 2, 3, 4, 5, 6, 7. Because it's at position 1, you don't have to specify the 1 out here. It has to be that way. So given that, what should be the name of this compound? I'll click back over to the slide so you can look at the potential answers. correct answer should be B. So we have 5-chloro, 4-ethyl. Now look, we had more than one carbon unit, right? So we have two carbons is ethane. It's a substituent, so it's ethyl. 4-ethyl, 3-methyl. And again, the order of those is alphabetical. So C is greater than E is greater than M. Even though the numbers 5, 4, 3 are descending, the order comes from the alphabet. 5-chloro, 4-ethyl, 3-methyl heptanal. So just before we close up for today's chat session, I want to just explain to you why you don't put the 1 there. I'm going to demonstrate that with a different compound that is an isomer. So see this compound now, I've moved the carbonyl over from position 1. I've moved it here. So the numbering of this chain stays the same. So the carbonyl, instead of being at 1, it's now at position 2. If it's there, what's the main functional group present now? This is no longer an aldehyde. It is what? So it's a ketone. So that's why if the carbonyl is at position 1, you don't have to specify it because it's implicit that says an aldehyde. But if it is internal to the chain, now it is a ketone, and you do have to specify it. So it would be the same sort of thing. So heptane, we would drop the E and then call it heptanone, so O-N-E. 2 specifies the location of the carbonyl, so 2-heptanone. The other part of it would remain the same. We would have 5-chloro, 4-ethyl, 3-methyl, 2-heptanone. So for some of these functional groups, you do have to specify the location of the main functional group. For some, you do not because it's implicit by what the functional group is. So I strongly encourage you to, go through these workbooks. This is chapter 5 on nomenclature. There's a lot of good problems in here to do. Maybe we'll do some of those on Wednesday. We'll finish up these other functional groups just to give you a preview. There's a ketone. Now you have more than one functional group present. So which one takes priority? Well, again, we'll review that. Then we'll go to the acid, the ester, the amide, and the acid chloride. So we'll talk about those priority groups on Wednesday. In the meantime, please do a little bit of each of your Wiley Plus assignments so that you're caught up. If you have any questions, shoot me an email. If it can't be answered through email, we'll set up a 30-minute Teams invite. But other than that, we'll see you guys Wednesday.